Welcome friends. We know that when light travels from a denser to a rarer medium, it bends away from the normal. And when it goes from a rarer to a denser medium, it bends towards the normal. So I want to find out the refractive index of the denser medium based on the real and apparent depths of an object inside the denser medium. It's a very common concept. When you see an object inside water, you find that its apparent depth is less. So let me move right away into the problem. Consider this as the surface of separation of the denser and rarer mediums. Let's say that this is the rarer medium air with a refractive index of 1, and this is the denser medium with refractive index of with the refractive index of mu. All right, fair enough. Now let me draw the normal like this, and consider that there is a ray of light which goes like this, and this is the object O. The ray of light is going with an angle of incidence I. Alright, and then this ray of light hits the surface of separation and it bends away from the normal. It bends away from the normal, and it bends away from the normal at an angle of refraction R. Fair enough. Now say that the observer is here. This is the normal, so he is not very far away from the normal. Alright, this is the first situation, the first scenario that I'm considering. Now by Snell's law, I know that mu into sine I is equal to 1 into sine R. Fair enough. And therefore mu is equal to sine R upon sine I, and that is equal to R upon I for small I and R. So when the I is close to the normal, the small I and small r are small, and therefore their signs are equal to the ratio of the angles. That's a very common concept. So we have got this concept that this mu is equal to R upon I. Now let's understand what exactly this is, this R upon I. So R upon I for small r and I can be written as tan R upon tan I. And let me, if I move this backward like this, and if I draw a normal here, then I find that this is the apparent depth d dash of the object, whereas this is the real depth d of the object. Alright, now if I move this backward, then this angle, our opposite angle, this will also be R. Now let me form a triangle. Let this be one triangle, alright, and let this be another triangle. Now I know that this distance is constant for both B, so tan R by tan I will be equal to, considering this figure, it will be equal to B upon d dash divided by B upon d, and that will be equal to d upon d dash. So this R upon I, which was the refractive index, is actually d upon d dash. So mu is equal to the real depth upon the apparent depth, and this is a very important concept which is only true so long as I and R are small, that is, the observer is close to the normal. But let me consider another situation where R and I are big. That means, consider once again, let me draw the diagram, and this is the surface of separation, this is the normal, alright, and this is the object O, but this time the observer is here, quite away from the normal. So when I consider this as the object O, in that case the ray of light will go like this, and then it will bend away from the normal in this fashion. So the angle of incidence will be I, the angle of refraction will be R, and both I and R are large, so that small I and small r approximation can no longer hold true. Even now Snell's law is applicable, that is mu will be equal to, this is mu, this is 1, so mu will be equal to sine r by sine I. Alright, now let me consider the graph of sine and the graph of tan. So if I consider that graph, this is the graph of sine. Alright, it touches a peak value of 1 at pi by 2, and this is the value of tan. It's here and then it moves away very rapidly, moves to infinity at pi by 2. So when you consider I and R, I is large, R is large, and R is more farther away from I than in the first case. So let's consider that here we have R is here and I is here. Alright, this is R, this is I. So if I consider their signs, then sine R by sine I is not a very large value. Say it is 1.5. But if I consider them on the tangent or the tan graph, then tan R by tan I will be a huge value. Tan R by tan I will be a huge value in this case. So what exactly is tan R by tan I? We already know that it is the real depth upon the apparent depth based on the geometry which we calculated in this scenario. So the real depth by apparent depth will be a huge quantity, whereas the refractive index is not that much. You understand? Let me draw a normal here, and this is the real depth of the object, and this is the apparent depth of the object. So as you can see that the real depth is huge compared to the apparent depth. So this illusion, optical illusion, will make you feel that this surface is having a huge refractive index, maybe 5, 7, 8, but the refractive index of this medium is 1.5. And the reason why this is happening is because you are looking away from the normal. So whenever you want to judge the refractive index of the medium based on D and D dash, look close to the normal, not away from the normal. So this is the concept that I wanted to share in this video. Stay tuned to Neon Statics for more. Thanks all.